Hi, and welcome to today's session on probabilistic predictions and calibration. First, we're going to start with a short reminder what we look at when we talk about supervised machine learning. So oftentimes we want to predict a value given the data. In classification, this can look like a point prediction, which would be, in our fruit example, would be just lemon. Or in a regression case, it could be a very specific value like 2.15. Those point predictions, as we call them, they actually just predict you one single value that is either the label in the classification setting or just the value in the regression example. However, those point predictions do not encompass any kind of information about the uncertainty that is in this prediction. So one way to adjust that, or one way to represent uncertainty, would be, for example, probabilistic predictions. In our classification setting, we can, for example, look at some churn prediction where we want to predict whether different customers stay with the company, or they stay with a product, with a subscription or whatever, or they're gonna leave. If we just look at the point prediction for those three different customers, A, B, and C, we can see that the model always predicts stay. However, we can see that the probability that a customer is gonna stay varies a lot between those the three different examples. Customer A has a probability of 99% to stay, B only 75%, and C only 51%. And now the big question is, even though the point prediction is stay for every of those customers, the big question is, should all those customers be treated in the same way? Do they actually represent the same stay in a way? Or is the information about the uncertainty of the prediction or the likelihood of the customers to actually stay, is this of interest? And I would argue it actually is of interest. And now that we have this kind of probabilistic prediction, so not only yes or no, stay or leave, lemon or pear, but a probability or like a score with it, one big question is the score that we get actually calibrated? And a prediction is well calibrated if we predict a confidence P, then the prediction will also be correct in 100 times P% of the time. So for example, let's go back to our fruit example. If we have the probability that the actual outcome is pear for 75%, then actually in all those examples where we predict those 75%, we actually also want in 75% of cases to for this prediction to be actually true. So for example, if we predict for 4 different fruits that all predict 75%, in actually 3 of them we expect to have actually the pear. One problem of modern machine learning algorithms is that they are known to be miscalibrated. So they actually give us scores that are mostly very overconfident. This usually comes from, for example, in deep learning models, from the way they are trained, that it actually encourages predictions to be very extreme and very confident. However, if we go back to our motivation why we should care about uncertainty, for example, in medical diagnosis cases, we would be very much interested in having properly calibrated predictions. And one way to check that is, are they calibrated? One way how to measure this is the expected calibration error. So if we, for example, look on the plot here on the left, we can plot the confidence on the x-axis. So for example, our 75% from the example before would be exactly at 0.75 here on the x-axis. And then for all the examples that fall in one bin, we measure then the accuracy. So how correct are we on those predictions? And for example, if we are in this bucket of 75% confidence, however, we can see that here the accuracy is only about 0.5. We see that we have this red gap here. This gap between the actually perceived accuracy to the expected accuracy that we would need to be well calibrated is a calibration gap. And now we can just measure the weighted average of those calibration gaps to get the expected calibration error. So if we look here on the math formula, we can see we are summing up from m is 1 to big M. So this is the number of buckets that we have. So in our case, we have one bucket from 0% to 20%, 20 to 40, 40 to 60%, 60 to 80, and 80 to 100%. So we have 1, 2, 3, 4, 5 buckets. And then we count the number of items that actually fall in each of those buckets. So we get the weighted average because, for example, since we know our models or many machine learning models tend to be overconfident, so there will be more examples that lie in the bucket between 80% and 100%, for example, than between 40 and 60. And we want to actually acknowledge this difference in size of the buckets. And then we just measure the absolute difference between the accuracy and this confidence. And with that, we get actually a very nice interpretable value, the expected calibration error, that can actually already tell us a little bit about how certain we are how well calibrated the examples are. In the next example, I'm going to show you a calibration plot for the Cypher 10 and Cypher 100 datasets. Just that you know what we're talking about, I show you here some images out of them. So those are two datasets that are very classical computer vision image classification datasets. Cypher 10 is called like that because it has 10 classes. Here you can see airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And Cypher 100 is an extended data set that has 100 classes. And because all 100 would be a little bit too much, I just showed you some of them. So there is, for example, dinosaur, apple, boy, cup, and so on. Okay, and now we can look at the calibration plots for the Cypher 100 dataset. So if you just train it on a very regular ResNet, it's uncalibrated, you can see that you actually have this overconfidence. So for example, here in the second to last box, we can see that the blue bar is much lower than it should be. We can see we have like a large red gap. And one way how to improve this miscalibration is to actually do something that is called temperature scaling. So we basically scale the predicted outputs by a certain value, that's t here in this case. And this helps us to actually improve the calibration. So we train this t on, or we learn the t on a held out data set. We can use it to actually match the predicted scores to the actual accuracy, and this helps us to get better calibrated outcomes. So we can see in the previous example we had a expected calibration error of 12.67, and we can reduce that to 0.96 by just using a very simple calibration technique. Okay, why does calibration actually matter? Once we have calibrated probabilities, they become interpretable. So a prediction with 80% confidence is correct about 80% of the time. This is actually just the definition of calibration, and it very much helps it to become interpretable. Calibration also supports risk-aware decisions because it enables a thresholding based on some meaningful probabilities just than this arbitrary confidence scores. So if we remind ourselves back to this Cypher 100 example where we had very miscalibrated scores, if you would say, for example, okay, we give those examples to humans that are that have a score lower than 80% or 50% or whatever, we can actually make meaningful decisions here because those scores are now calibrated. Also, proper calibration improves comparability across models. So those calibrated probabilities can now be compared, combined, or averaged. So we can, for example, use multiple models and actually see how the predicted probabilities change across those models because they all mean the same thing. Now, once they're calibrated, they represent something that is actually meaningful. Also, it enables uncertainty communication because we get an intuitive way to communicate this confidence to users and stakeholders. So as you see, those are all nice properties for calibrated probabilities. However, there are also some caveats. No, one more positive thing is still exists. Because calibration is also the foundation for many uncertainty-aware methods, it's often a prerequisite for decision support, active learning, and probabilistic forecasting. Active learning is a tool where you can basically decide which instances you want to have labeled in your example. So you basically continuously build up your data set in a way that those instances that are labeled are the most informative to you. So instead of, in our fruit example, labeling the same lemon for the 50th time, you can maybe have it from different angles, or you have it from maybe a different producer that looks a little weird, it has a different color or whatever. So you can label those instances that are more informative. We will look at active learning later on for human-in-the-loop machine learning as well. Okay, so now come the caveats of calibration. Calibration by itself is a population property, so it guarantees reliable probabilities on average again, but not for individual predictions, which might be important for certain applications. Also, just that because a model is well calibrated does not necessarily mean it's a good model. So calibration and accuracy or predictive performance are two very different concepts. And you can actually show that there is a way to have seemingly perfectly calibrated models that actually give you very little actual predictive value. So for example, by always predicting the class frequency, you will always get a perfectly predicted model. However, if you always predict the same thing, there is actually no value in the model itself. Calibration does not identify difficult cases, so it does not ensure that uncertain predictions actually correspond to mistakes. Detecting errors requires good discrimination, so proper accuracy or predictive value, and not just this calibration. So again, we can see that since it is this population property, the problems also move onto, for example, this good discrimination. Also, confidence calibration is only one notion of calibration. So if we have multi-class settings or class-wise calibration and label distributions, they also all are different concepts that kind of relate to calibration, but are not included in those very basic definitions that we looked at so far. Also, the evaluation is challenging because the expected calibration error depends on this arbitrary binning. So as we saw before, so we decided to have either bins from 0 to 20, 20 to 40, or bins of length 10. So for example, from 0 to 10, 10 to 20, and so on. And depending on how you exactly choose those bins, you can get very different results. Also, the expected calibration error does not necessarily behave the same for all different models. So even though we can have different models that have the same expected calibration error, they can behave very differently. So maybe for one model, the calibration is quite average over all the bins, and maybe another model is very, very bad in certain bins, but if those bins are the ones that we're very much interested in, this might be very problematic. Okay, thank you for listening. We acknowledge funding by DFG and copyright. Thank you, everyone.